Welcome to the third and final video of Chapter 8. Here we're going to estimate the population proportion. Now the first two videos in Chapter 8, we estimated the mean where sigma was known. Then we estimated the mean where we did know sigma, where we used students' t-distribution. But here we're going to estimate the population proportion when you have categorical data. When you don't have that quantitative data. Ordinarily you're going to look at some form of the proportion. Now in the population we use the symbol P to represent the proportion, but there's some category for a large group of individuals, and we want to estimate what the part is that's in that category. And what we can do is to use the sample proportion. That's the P with a dash across the top of it. We say P bar, but we're going to use P bar as the point estimate for P, the population proportion. Now the form is going to be the same as it was for the other two cases. We're going to have the point estimate plus or minus the margin of error. Now the point estimate for the population proportion is P bar. And you add and subtract the margin of error for the interval estimate. Now the margin of error is going to be the z-value times an approximation for the standard error of the proportion. The way that you get the approximation is you take the square root of P bar times 1 minus P bar over n. We're not able to actually use the standard error of the proportion because we're trying to estimate P and we don't know what it is. Now in order to use the z in the calculation, we have to have a situation where we can use the normal distribution. And the rule of thumb that says it's okay to treat the sample proportion as though it's normally distributed is that n times p is at least 5 and n times 1 minus p is at least 5. Unfortunately, we can't check to see if we meet those rules until we get our estimate for P. This is very close to doing an estimate of the population mean. It's just a different formula. We're going to use the z, and we're also going to use the standard error of the proportion. Now the formula for the standard deviation of P bar, or the standard error of P bar, is the square root of P times 1 minus P over n. Now the issue is that we don't know what the value of P is. We're trying to estimate it. So the best estimate that we can use is the value for P bar. So we're going to approximate the standard error of the proportion by taking the square root of P bar times 1 minus P bar over n. But we'll multiply that number times z to get our margin of error. But the interval P plus and minus the z value times this approximation for the standard error is going to contain a certain proportion of all possible sample proportion values. And this is the way that we can get that confidence interval estimate. But it's very, very similar to what we've done previously. It's just a different formula. Now the flowchart will work just fine for this case also. We have a problem to where we're trying to estimate the proportion. Okay, is n times p at least 5 and n times 1 minus p at least 5? Well, there's no way we can tell because we don't know what the proportion value is. So we just have to assume that that's going to work out for us. And then we can go to the formula for the confidence interval estimate. You take the sample proportion plus or minus the z value times an approximation for the standard error of the proportion. You take the square root of P bar times 1 minus P bar over n. The textbook uses the subscript alpha divided by 2 on the z value, but it's the same situation as it was for estimating the mean. You have a level of confidence. The complement of the level of confidence is called the level of significance. The symbol for that is alpha. Now the level of confidence is going to go in the middle of the z-distribution. That means that the level of significance is going to have to fit in the two tails. Half of it goes in the lower tail, half of it goes in the upper tail. But we just figure out what that z-value is that separates the upper tail from the middle part and the lower tail. Now we're going to multiply that z-value times the approximation for the standard error of the proportion. We take the square root of p bar times 1 minus p bar over n. Now when you multiply that approximation for the standard error times the z-value, that's your margin of error. And all you have to do is add and subtract that number to your sample value to get your confidence interval estimate. It's just like what we did before, it's just a different formula. Now this is the problem that we're going to use to exercise the procedure. Political Science Incorporated, they do polling, and they're looking to see what's the proportion of people that are voting for certain candidates. So here they're using telephone surveys to ask people who they're going to vote for. In this case, they contacted 500 voters, and they found out that 220 of them favored a certain candidate. So we can calculate what that sample proportion is. Just take the 220 and divide it by the 500. Now they want to use that sample information. They want to use that point estimate to develop a 95% confidence interval estimate of the true proportion of the population of the registered voters that favor that candidate. So all we have to do is just plug the numbers into the formula and do the arithmetic. The p-bar value is 220 divided by 500, which turns out to be 44%. You get the z-value from the z-table. At a 95% level of confidence, you're going to put that 95% in the middle. The value of alpha would be 5%. Half of that goes in the lower tail, half of that goes in the upper tail. If you have half of that, which would be 2.5% in the upper tail, then there's going to be 97.5% that's below that. So the part that separates the upper tail from the rest of it, there's 97.5% that's below that, and that's what you need to look up in the interior of the z-table. But you find that 0.9750, and it corresponds to a z-value of 1.96. So that's the number that we're going to plug in for z. So we take the 220 divided by 500, the 0.44. We're going to add and subtract 1.96 times the approximation for the standard error of the proportion. We take the 0.44, our estimate from the sample, times 1 minus that, divided by the sample size, 500, and take the square root. Now when you multiply the 1.96 times the square root of 0.44 times 1 minus 0.44 over 500, it's approximately 0.0435. But the 0.0435 is the margin of error. Now we're going to add that and subtract that to the sample value, the 0.44. Now when you add it, you get 0.4835. When you subtract the margin of error from the 0.44, you get 0.3965. But we're 95% confident that the proportion of all the voters that favor this particular candidate is between 39.65% and 48.35%. Now this concludes the coverage of Chapter 8, Interval Estimation. We covered how to estimate the mean where you know the value of sigma, how to estimate the mean when you don't know the value of sigma, and how to estimate the proportion. The next chapter is going to get into hypothesis testing, which is another form of statistical inference.